My name is Maurits van der Plas, and my co-speaker is Victor de Graaff. We're presenting today in behalf of the Effective Data Foundation. So there's an initiative about sharing best practice in data and AI, as the name says so. It's a non-for-profit collaborative, and together with thought leaders, we figured, okay, what can we do to enhance the audience, to give something back to the community? So we decided to set this up, the Thursdayta. The idea is that once a month or so, we give a presentation about effective data foundation, different data and AI subjects, to give back to the community and grow a sort of community audience as such. So today is our first run. It's a dry run, so we're trying to see, okay, is this the right audience? Is this the right mechanism to reach out to people? So therefore, forgive us if we're still trying to figure out how things work. As mentioned, Effective Data Foundation not-for-profit collaboration. We have several certifications that are offered by quite an amount of training bodies and organizations. So far, it's about data literacy, AI, data visualization, and we're growing this initiative. Also, there's quite a few people following the training through various partners, and we're also trying to grow the initiative of the Effective Data Foundation. Just a little advertising in advance. So we have various courses now that fit to the Effective Data Foundation, and we also try to collaborate and elaborate in the field of data and AI in general. Therefore, enough for me, and I will now move to our speaker, Victor, who will give some insights about AI. It's a popular subject right now. Probably you heard a lot about it, but yeah, of course, Victor can tell it better than anybody else. No, I'm joking. I'll be your host, and I'll give the mic now to Victor. Victor, can you take over the presentation mode?
Yeah, I already did. Sorry.
No worries. So perfect.
I just was a bit fast.
Okay.
Can you see me?
All yours. Yeah, I can see you.
Yeah, all right. So welcome, everyone. I'm Victor de Graaff. What I have done in the past is basically everything in the field of data. I will start my journey where I will take you along in what I did during my PhD. So there I made a recommender system for holiday homes. And basically what we did there was we looked at GPS trajectories and we looked at social media data and combined those. And based on that, we gave the perfect recommendation for holiday homes. So when I tried it out myself, I got a recommendation to go to England. I said, why would I want to go to England? It's cold there. It always rains there. The food's terrible. So why would I want to go to England? But what the idea was in my recommender system was to see why the recommendation was there. And then it told me that it thought that I would like Hadrian's Wall there. And indeed, I love Roman architecture, and that's very much what was in my profile. So from that on, I could deduct, I actually do want to go to England. But that's basically my journey. From there on, I went to ING, did fraud modeling there. So we stopped a lot of fraud using machine learning. Then I went on to Heineken, and 4 years ago, I founded my own business, D-Data, where basically we do everything in the field of data, from AI to other forms of data science and data engineering. We give a lot of data trainings, very often also the Van Haven material, which is why I am joining here. And that's just my journey, but there has been a journey for the rest of the world as well. So feel free to jump in if you recognize this image. Anybody ever seen this before? Any movie lovers here? Especially the older movies? See if I can grab the chat here. Is there anybody? Let's see if anybody knows. We have some information in the chat. No, we just that somebody is using AI to read the minutes of this meeting or to create them. Nobody recognizes this movie?
Need some typing. I also don't
Yes.
HAL 2000.
Yeah, HAL 2000. Well, add another 7,000 and you're entirely correct. So HAL 9000. It was a spaceship, and the people inside the spaceship, or actually HAL 9000 was the computer inside the spaceship. Yeah, close enough. And what you see here is that actually the people inside the spaceship, let me see, let's rerun the video. They're basically just playing chess while the system is telling them everything they need to do. And this movie is from 1967. So this already shows you how long ago people actually had a sense of what would be possible if computers got smarter and smarter. But I'm from 85, so this is more my thing. And I'm sitting in the way of Michael Knight right now, so let me switch to the other side. And let me co-pilot him in writing Kit. Does anybody remember Kit? Probably a few more people here. And Kit was just his car that was a self-driving car. And the scene that you see here is actually the first scene where Kit starts talking to Michael Knight. And well, he freaks out entirely because he's never seen a self-driving car before. What I like about this is that, again, this is quite close to what the future has become. If we look at a Tesla now, it is quite similar. In fact, they actually want to use steering wheels that look somewhat remotely similar to the one used here, but they're not allowed to, at least not in Europe. In Europe, steering wheel has to be round. Although I have heard stories that by now the other steering wheels are coming to the European market as well. But the idea is that the fully self-driving car, again, in Europe, not everything is allowed. So, for example, you're not allowed to summon the Tesla to come driving to you, whereas in the US, this is allowed already, which is especially nice on very tight parking lots, especially if you have a little bit bigger belly. So I guess that's why the American market allowed it first. All right. And if we get a little bit closer in time, so here we're talking about the 80s, let's jump on to the 90s. Who remembers who these two people are? I'll be very impressed if you know both of them, of the people. Any chess fans here? I see a no. No chess fans?
So Ton says Kasparov versus Deep Blue.
Kasparov versus Deep Blue. Oh yeah, I was already reading one further. Yeah, indeed, this is the competition that's going on here. I think I was just still in grade school or just in high school. I did like chess as a kid, but I didn't get very far because I always thought like, hey, standard openings, everything. So this game has been played to the end already. Nothing to learn here anymore. I rather had games where luck was a little bit more involved at that age. But when I look at myself now, I love the games where there's absolutely no luck involved. And chess is definitely one of those games. So by now I'm super addicted for the past 2 years. And in fact, we are doing within our company, we do competitions in who's the best. But unfortunately, if you are the best at chess, you're automatically every time the best at chess. So it's not like in football where you sometimes get lucky. Ball on the post, ball just outside the post can make a big difference. That's not how chess works. So if you're good, you win. But this made quite some change because this was one of the first times that a computer was actually better at something than a human being, which was considered extremely complex. And also, a computer is not capable, or especially back then, was not capable of seeing the game all the way till the end. So they had to kind of stay at where like 2-3 moves ahead, and they got smarter and smarter, looking more and more moves ahead. And this was the first time that actually the best human being when it came to chess got beaten by a computer. And by now we actually consider it to be normal. So we just find it normal that Stockfish, which is the best chess engine at the moment, is better than Magnus Carlsen. And there are other games like Go, for example, which is even more complex for a computer, at which the computers, like the guys from Google, are already beating the winners now. The nice thing about this is because it's a really visible comparison. Like you really, at the end of the game, you have this this clear winner. And in other fields, it's not so visible. For example, that people are now better, or computers are now better at detecting breast cancer than radiologists are. This is something which is not so visible to the entire world, but it is true. They are outperforming them now, the best human beings in that field. And many more fields are taken over by computers that they are better at it. Oh, sorry.
Need 1 second. Sure. What time are you looking for around? At 12 p.m. We do not have a 12 p.m. available. The closest we have to that is a 1:15. Do you have anything between 10 a.m. and 12 p.m.? Depending on what service she would like. What service is she looking for? Just a woman's haircut.
Oh. All right, I wanted to. I mean, it's
Just a woman's haircut for now. Okay, we have it 10 o'clock. 10 a.m. is fine. Okay, what's your first name? The first name is Lisa. Okay, perfect. So I will see Lisa at 10 o'clock on May 3rd. Okay, great. Thanks, great. Have a great day. Bye.
So you can hear the people cheering towards the end. This is not so long ago. This was 6 years ago. By now, given that we have ChatGPT, we find this super normal. But 6 years ago, this was revolutionary to be able to talk, like to have a conversation between computers and human beings at the same time. And I like this video so much because it really shows how fast things are going. Like 6 years ago, people were cheering in the room, and like you just heard the beginning of the cheer, but it was actually really an eruption of cheering because people were so impressed. And by now, it's just like, yeah, of course, computer can do that. Like, we have text to speech, we have speech to text. Surely we can do this. So this shows us how fast things are going at the moment. And what causes it now that it goes so fast? So one of these things is that there are sensors everywhere. Everybody on their phone, you already have so many sensors. Like you have your accelerometer, you have your GPS sensor, you have your microphone, you have your camera, you have your NFC chip. There are so many things that you can use on your phone already, just your phone. All these things, but now people are wearing smartwatches and all kinds of wearables. And a lot of devices have chips on them. Like if my garbage can gets picked up outside, if the truck drives by, they see that it's actually my garbage can. So I get an invoice at the end of the year, and they tell me every single date on which garbage can was outside in front of my house, and I have to pay for every time I put it outside. If I don't put my garbage can out because I'm on vacation, I don't have to pay for it. So there's sensors everywhere, and all this data is collected and used and analyzed. You have this OV chip cards. And when these were introduced, it was a super controversial thing to do. Like, but what's wrong with the good old strippencard? And so which was the paper version of this card, which we used to have. And by now, everybody just accepts it. Like, we're like, why did we use these paper cards? You could just put a sticky tape over it and you could stamp it again and again and again. So first of all, we have sensors everywhere. Now we have data everywhere. Secondly, we have computing power everywhere. So I'm sorry that I come up with an old video again. I just really like using old videos to show where have we come from and to kind of give people an idea, like, all right, this is not so long ago. Like, this was in the 90s, the introduction of the first Mac. And if we look at this now, we think like this is crazy old, but either we are crazy old then already, or things are just going super fast. Like, this screen, what kind of a resolution was it? Everything is just totally different now. We are just used to extremely high resolution screens, super flat screens, everything smaller, faster, more computing power. If you look at a CPU, which is like the processing unit inside your computer, which has been there for ages. So these computers already had a CPU. These things, at the same time, they can make up to, let's say, 4 calculations. If you have a quad-core processor, which is quite common these days, you have 4 things that your computer can do at the exact same time. A little bit modern computers will have 8, but that's it. If you have a GPU, which is like a video card, which we used to use for playing video games, but by now they're so expensive that you just use them for crypto mining and running machine learning algorithms with them. But they can run easily up to 2,000 calculations right at the same time. So this computing power has increased enormously over the past years. And the third one, so the first one was sensors everywhere. The second one is computing power everywhere. And storage is extremely cheap. But the third one is algorithms. And these algorithms that are there, so what you see here actually is what you call a reinforcement learning algorithm. Basically, you just run a lot of simulations and the computer gets smarter itself. So you don't really tell him what he needs to do or how he needs to do it. You just give him a score of how well he did, and he's going to try to increase that score again and again. So what you see here are simulated cars that try to get farther and farther. Basically, all they do is like they look ahead, they look left, they look right, and they look to the front, and they see like, okay, these are the distances until the wall. And you don't even tell him that he shouldn't be colliding with the wall. You just give him a score as a feedback, like, yeah, this is how well you did. So now you got 1,000 meters far, now you got 1,200 meters far. And he's going to try to optimize that score to get it higher and higher. And basically what you see is that the computer, without that you have to program everything he needs to know about taking curves, what speed to take it, how much to steer, he's just going to learn it by himself just because he gets an evaluation after everything he does. He just always gets feedback after every run. And these algorithms, they've been around for a while. The deep learning algorithms, so the algorithms that use very large neural networks, they've been around since the 50s, 60s of the previous century, but they just didn't have computing power or data sets to run everything on. I mean, who still remembers the floppy disk, which could hold up to 1.4 megabytes of memory? If you think about it now, that's not even half of a song. It's not even a quarter of a picture on a phone with a high resolution camera. That's all it could hold. And we used to think, yeah, it's plenty. I got all my homework from the past 3 years on this floppy disk. So all that together, that makes sure that we have this eruption of AI, and that's why it is so booming right now. But what you see in the media a lot is AI as ChatGPT. So we're talking a lot about generative AI. So we have these chatbots, we have these picture generating bots, we have by now video generating bots, all kinds of automatic stuff, which is not super specific for its purpose. For example, If you ask ChatGPT about math, he'll help you. If you talk about physics, if you talk about law, if you talk about how to have a simple conversation with someone, if you want to talk about a specific book, he'll know it all. So this is not a very specific form of AI. It's very generic. You can use it for a lot of things, and the people who made it have no idea how it's going to be used in the end. It's different when you talk about more specific AI. I have a couple of examples coming up of projects that I did, but I'll give one up front already. So, for example, at the Department of Transportation in the Netherlands, called Rijkswaterstaat, we created a model that predicted at which temperatures bridges would get stuck. Because a bridge is mostly made of steel. That's the most important component of any bridge. And when steel expands, it gets larger, and when it expands too much, then the bridges get stuck. And there's a solution for that. It's called a finger gap, or in Dutch a vingervoeg. And what you see is that these gaps, they can close because they can close like this. If it's too hot, then they close a little bit more, and if it's too cold, it's more like this. That's basically the idea. But if it gets really too hot, at some point it just gets stuck. It cannot get any farther. With a lot of force, you can still get the bridge open, but you can definitely not get it closed anymore after it expanded like that. So basically, you just don't open the bridge anymore, and boats cannot get through. Well, this is something they would really like to avoid, especially because boats can be quite expensive to have to wait. So what they do is they cool the bridges from underneath with water, and we made a model that would predict at which temperatures these bridges needed to be cooled, and that was different not only per bridge but actually per part of each bridge. So sometimes the part of the bridge that moved had to be cooled at a different temperature than other parts of the bridge. Actually, it was kind of a given. So what we do there is basically you're going to try to predict a number, and in this case, what we see here in the video is you have a handwritten number, which is probably a 5, and then a model will be trained to help us, telling us that it actually is a 5. So that, for example, you can scan all kinds of paperwork automatically. If somebody fills out his phone number somewhere, you can use models like this to read that phone number that was written. Or even a CAPTCHA if you want to do some automated stuff on a website that doesn't want to be treated in an automated way. That actually works by now. You can just ask ChatGPT, what does this CAPTCHA say? Although I recently found out that they are getting smarter at it to limit that type of usage. Anyway, so what you do here is you have a very clear input, you have known outputs, and you try to find a mapping between those two. So that is one way. We call it classification. Even though it's a number that we are trying to predict here, we still call it classification because there are only 10 numbers that can actually be handwritten, 0 through 9. Other numbers where we actually really talk about a number, like for example, the value of a stock over time, or in this case, the number of ice creams being sold given a certain temperature. We can start trying to predict the number of ice creams that will be sold on a certain day, given a certain temperature. What you see here, the green points, they are the actuals. That's the data that the model is trained on. And the black line, that is the model. That is basically the prediction that it will give. So if, for example, it is at a day, it is 20 degrees Celsius, then roughly we will get 50 ice creams sold as the prediction. And how did it get to this line? How did it get to the model? Basically, it tries to reduce the gap between all the points and the line as much as possible. And a big gap between the line and the point is generally perceived as worse than the ratio of its distance. So let's say a point is twice as far away, then we find that 4 times as bad as if it was only like 1 point away. So we try to minimize the number of large errors. And this you call regression. So where we had here classification, we tried within a limited set of numbers that can be written. So there are 10 classes in classification in this case. Here we try to find a value, a numerical value, and we call that a regression model. That's the second type of models. Third type of models is clustering models. What I always warn people about is that if you make a clustering model, what you don't want to reach is that the clustering model says exactly what you told it that it should say. If, for example, you create a data set where in the data set you have, for example, the number of square meters in a store and the number of parking places, and you're going to run a clustering model on it, it's going to tell you, yeah, this is a really large store with lots of parking places, because that is exactly the information that you fed it. So it's very important that you find the right thing to cluster on. And an example of what we did with our company for what gave really good clustering was for Vrumona, which is the soft drink beverage supplier of Heineken, or at least it used to be, which basically sells Pepsi and CC and everything that's not Coca-Cola, but it is famous. That's basically all sold and created by Vrumona in the Netherlands. And what we did was we looked at out-of-home business, so everything you drink outside your house, so the restaurants, bars, gas stations, soccer clubs, stuff like that. We looked at all their data, we looked at their sales data, and we looked at which product was all sold very often. And based on that, we made the clustering. And now we found out that, for example, Subway is actually very similar to a lot of gas stations where you can put a cup underneath and like the soft drink comes out automatically. But they didn't look like gas stations, for example, that sold the plastic bottles, the PET bottles. But they definitely didn't look like restaurants, because Subway traditionally is classified at Vrumona as a restaurant. But that makes no sense, because at the restaurant, they normally give you the glass bottles, and they don't sell any glass bottles. So if you're going to say like, yeah, based on your cluster, we see that you should be selling more glass bottles, and Subway will just say that's nonsense. We don't do glass bottles, so don't compare us to other restaurants where they do that fancy stuff. So, and what you see here is actually one of the most famous algorithms for clustering. It's called k-means. Basically, what it does is it starts at random points. And after starting at such a random point, so it makes 3 clusters, but it keeps moving towards the new center of the cluster. So in every iteration, you see several iterations in this animation. Every time it takes the new center of the cluster and it lets it move until what we call it converges. It no longer moves, it's happy, it's sitting steadily there where it is. And now it has found 3 clusters. Why 3? Because we told it to do so. In k-means, you have to give the number of clusters up front yourself. And very often, how many you take is, for example, decided by how many people you have in your sales force. You say like, yeah, I have this area and I want to split it up in a logical way over several people. Okay, how many people do you have? 3. Well, okay, you make 3 clusters. So very often it's decided by the operation how many clusters you can actually handle. But sometimes it isn't. Sometimes you just want to make a sensible cluster and not have points that are very far away from each other. For example, this yellow point here at the right bottom, you don't really want that to be in this cluster, if at least I would say. So there are other algorithms that actually say like, no, if points are too far away from each other, that's when I make a new cluster, which would actually possibly make this one very large cluster, or say like these points that have some white space in between, they might get their own cluster. depending on how high you set the threshold yourself for whether or not something still belongs to the cluster. But for example, this point and this point and this point here, this point right there, they probably wouldn't belong to any clusters and get their own cluster then. So this can be done with a lot of different techniques. There are a lot of different algorithms that can do either of them. You can do the classification, you can do the regression and the clustering. You can use a lot of different algorithms for it. But especially for the first two, you can also use deep learning. In deep learning or neural networks, basically you speak of deep learning when the neural network has enough layers. So what are layers? Well, basically, if you look in this animation here, what you see is that you get all these layers of, right, let's pause it right. 1 second, not get ahead of ourselves. So you see all these different layers. Typically, we would say layers you draw on top of each other, but in this case, we always draw layers from left to right. And these are the first layer is always your input layer, and the last one is always your output layer. So your input layer, for example, let's say we do the classification of the handwritten number, then on the left-hand side, you see the pixels of the image, in this case 3, which is probably not enough to draw any number, but we need to visualize it somehow. So every pixel gets its own neuron, as you would say here, input neuron. And on the output side, you would have as many neurons as you have classes. So for example, if you want to classify a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then you probably want to have 10 layers here. Preferably, I always say add an 11th layer for not a number, because otherwise an A and a 4, they look quite similar. So the score for a 4 would be quite high already. And you don't really want that. So you want it to be possible to say not a number just as well. So I would always suggest create one more, like nothing found. If you have dogs and cats, well, at some point you're going to show a picture of, let's say, a koala bear. You don't want him to say like, oh yeah, it looks kind of like a cat because it has ears. So that's why you want to always give some space to the model to get rid of nonsense. And then in between you have a lot of layers. And if you have a lot of layers, we talk about deep learning, and otherwise we don't talk about deep learning, then it's just a neural network. And what it will do here is it will create lines between all these layers, but they always go from left to right. They never go within a layer. So there are never lines between here. And that is the reason why it's mathematically still possible to at some point solve it. And what happens then, oh, still not a snake. What happens is it assigns a weight to all of these edges, as we call them, these lines, called edges. It assigns a weight to it. And the higher the number here, the more impact this neuron has on that one. It can actually also be a negative number. Then also the more negative the number, the more the impact is. The value that comes out here gets thrown into a mathematical function, and that gives us a new number for this neuron then, and that gets distributed to the rest of the network. So how do you get to these numbers? You don't, the computer does. The computer gets all these nice values out. So what can we use it for then? Well, all kinds of useful examples and playing Snake. Has anybody here ever played Snake? On phone, Nokia 3210, 3310, 8210?
Of course.
Yeah. So how many buttons could you push at one moment?
It's one at a time, right?
Yes, one at a time, but how many choices do you have at any point during the game?
up, down, right to 3? No.
The correct answer is 3, but we're not there yet. So the reasoning is not, we're not there yet. So I'll give it away a little bit. So basically, when you are going to the right, you can go either up or down, or do nothing. Those are the 3 possible inputs at that time. You cannot go to the right because that's the same as doing nothing. You cannot go to the left because you would bump into yourself. You actually, depending on the version, you actually die if you push that. But you could also play using 1 and 9 or 3 and 7 for the real pros. Like the others played with 2, 4, 6, 8. But 1 and 9 was for the real pros because you could use both thumbs and really get a cramp. And 3 and 7 were just the same, because if you were going right already, then the 9 couldn't mean right anymore, so it went down. And if you were going right, you would push 1. You cannot go left, so it would go up. But also you have the do nothing possibility, which basically gives us 3 possibilities at any given moment. Yeah. So Ton actually had it correct. Nice. And if you train a model now, this is called a reinforcement learning model. So this is like a last type of models. What these models do is it tries to teach itself what to do. And it's exactly the same as with the cars I showed before. That's also a reinforcement learning model. So it learns by itself. And you see here that there's a lighter gray box and inside a darker gray world. And the reason for that is because the video that I snipped this from is showing that it's basically impossible to model the entire world of Snake. And the entire world of Snake is not even that large, right? Like how many possible positions for the apple or for the snake are there really? It's not that many. But because you have this 3 possibilities at any field, so either the apple is there, nothing is there, or the snake is there, and we have so many pixels, like let's say it's like 40 wide and 25 high or so we have 1,000 pixels, we have 3 to the power 1,000. I don't even know how much that is, but that is a lot of zeros. So 3 to the power of 1,000 is impossible to model that all. And in fact, it is a little bit less, because it cannot be that everything around it, there's no snake, and then in the middle there's a snake. So there's a little bit less options, but this is the scale at which you should be thinking. So what they show here is like, we're going to model the snake world as just this, and we're just going to ignore the fact that there is an apple if the apple's out of sight. But we're just going to do the smartest thing here, so that at least we don't crash into ourselves, and let's see how far we get away with it. Has anyone seen this one before? I really hope so by now. And actually, I made him do this. I like this question. So I wanted him to expose his own strategy. So basically, the ChatGPT can do so enormous many things now. But the thing is, like, if I would do this in a video and I would explain it to you, then tomorrow already the video is outdated, because it's changing so rapidly. And basically, you can generate your images from here already, but you can also send it an image of your fridge, and you can say like, hey, give me a recipe for breakfast today, or which foods inside my fridge are healthy and which ones are, and they can just answer all kinds of questions like that simply based on an image. And that is, well, quite changing the world. You see a lot of questions. We get a lot of questions also, how can we train a model on our own data using ChatGPT, so that we can talk to our own data? We no longer have to create complex queries or whatever. We can just ask it like, okay, give us our top 10 customers, or we have a bunch of manuals here. I have a problem with my machinery. Make sure I troubleshoot in the most efficient way possible. Like, I don't even want to look for the manual. I just want to know that I have some trained chatbot which has read 1,000 models, not models, manuals, and he will know which manual to look in, and he will know which question to ask. So that's something which you see more and more by now. So if you are interested in these techniques, look into Streamlit, Weaviate, and ChatGPT. This combination of these three, that's going to change quite a bit. And ChatGPT is basically just an example of what you can do with GPTs. So I saw the question in the chat before, what model does ChatGPT use? What they use is a GPT, a general pre-trained transformer. And this is a type of model that is super useful for basically any generation of something. And in this case, it's text, but you can also create images with the GPT. And you can also, for example, create AutoCAD files. So AutoCAD is what's used in the industry to model any object, like a screw or whatever, anything that goes, for example, into a car. They will model it so that they make sure that everything fits and that everything follows the exact way that it was described. And if you would train, for example, a model on that, you can actually create new industrial hardware that you can just go to a store where you can say, like, hey, I typed in this prompt, this is the file I got back, can you please create this for me, or can you print this for me? So there are a lot of things going to change with ChatGPT, not just communication, but a lot of things will benefit from the popularity of ChatGPT, because GPTs are just super useful. For example, DALL-E actually uses a GPT underneath as well. It's just not a large language model then, but another model with different parameters, but the architecture, so the way the model is built, is the same. So what can we do with that then? Well, fun stuff like this. That is actually one of my break slides that I like to use whenever there's a break coming up. I like to have some relaxed atmosphere and put this one up there. So how did we make this? We came up with a prompt ourselves of stuff that I like. So a man in a canoe in a fjord at sunset is basically the prompt. And probably I did some extra things for my personal flavor, but these are the main ingredients of the prompt. And I created the first image of this little video, just the first image. I did this with Midjourney because it's my favorite model for image generation. I really like the style that it creates. And I gave this image, this one still image, I gave it to Leonardo AI, and I told it to create a moving video out of it. So every frame, except for the first one, is created by a different model than the first frame. And I think that is really strong as well, because how it, for example, how it extends this mountain, basically it keeps drawing the mountain based on the first image. I have never told the second model that there were mountains on the picture. It just understood it from the first picture and understood, yeah, I'm going to keep drawing mountain there. And it made the water wave, which is basically the reason why I asked it to do something in the water, because I know Leonardo is really good at moving water. What it's really not good at is moving straight lines. So for example, if you would have the same video of the Erasmus Bridge, and I might actually, yeah, I actually have it here, I do. That doesn't work so well because it has these straight lines and it should move without moving the straight lines, but the water behind it should move. Well, there it's having some trouble. In fact, the model that I used to create the image, the first image, also gave Rotterdam, where I come from, a second Erasmus Bridge. It's just not finished yet, but it's kind of nice that they gave us another one. Also, the Rotterdam, this building, where it looks kind of like the Rotterdam, is actually on the other side of the Erasmus Bridge. So there are quite a few mistakes in here. And that is exactly what you can see from this is, so somebody once asked me, can I not just take the picture that it created and go on reverse Google image search and see what it originates from? It doesn't originate from something. It just originates from the parameters that are set in the model, all the thousands of, or actually millions of pictures that it looked at while training. And it drew a new Erasmus bridge based on its knowledge of an Erasmus bridge, but it will always be slightly incorrect. So factual correctness, 100% factual correctness is impossible for AI because it doesn't use a database behind it. It just uses numbers. They're just numbers stored somewhere and not the actual footage that it was trained on. This is one of my personal favorite AI generated things. Watch out for those people who are using headphones.
Mij pakt dit geluid nog niet. I don't have the sound yet.
You don't hear the sound?
No. Before with other visual you did, I could hear the sound. The other animation, the first one. Now I can't.
I did switch to music mode, so let's see if it changes anything, but otherwise I'll just sing.
Now I hear it. Johnny Cash.
All right, I'll stop torturing you there. So basically they use the same techniques as you would to create this deepfake of his voice. And for a lot of people, there's a lot of data available. They actually recreated, not using AI by the way, they recreated Angela Merkel's fingerprint just of the super high resolutions that all the press agencies have online. So pictures that everybody can look at and that you can buy for your website if you have a news article or whatever. So just from those images, they were able to recreate her entire fingerprint. Well, if you apply AI on top of it, you can actually really make videos and make people say any kind of thing. And by now we're getting kind of used to it, that this is a possibility, that you can deep fake people in flattering or less flattering situations. And we have to watch out more and more for it. Today is the election day, so that's actually a nice moment to think a little bit more about stuff like this. And it's very dangerous if people start sending out videos as if they were real. People start reacting and changing their behavior because of these videos. So let's get to some more fun stuff. This is yours truly in two different ways. I used two different models to create a Barbie version of myself. I think if we would have gone for the left-hand side, it wouldn't have taken me 7 years to get married with my wife. I think it would have been done after 7 weeks. The right-hand side, a little bit less, maybe. a little bit more time. It's kind of fun to see how important it is, what data something is trained on. So it makes it really visible. I'll move to the side a bit. That's really, it makes a huge difference what you train a model on to see what comes out then. And that doesn't only go for fun stuff like this, but also if you, for example, you have the more ethical sides of AI, when we're talking about bias in a model, this can get quite dangerous if people, if they train models on, for example, the way people look at fraud. whereas the people who looked at fraud in the past might have a racial bias themselves. So yeah, you should always really watch out that whatever you do when you're modeling something, that you don't describe people from a certain group that you don't want to separate more than that you actually do the thing that you're trying to do. Like, for example, fraud detection. And fraud detection is a very painful thing, but it can also be reading resumes in an automated way. It can be quite dangerous if you benefit only those who are already benefited a lot in the past. Another way of using AI is to do object detection. So let's show what we did when we just opened our office in Den Bosch, which is famous for the bossenbollen. Every time I say to someone like, yeah, you should come to Den Bosch, they say, yeah, but there better be bossenbollen then, which are these days.
We kunnen er bijvoorbeeld obstakels mee detecteren op de weg. Wat makkelijk is om bijvoorbeeld ongelukken te voorkomen. Als we het computermodel geleerd hebben, dan kunnen we eigenlijk video's uploaden waar bossenbollen in zitten. En dan wordt eigenlijk door het computerprogramma gedetecteerd waar de bossenbollen zich bevinden. Kijk, deze ziet dus wel inderdaad rechts is hybrids vraag. Dat is zeker geen bossenbol. Dat is geen bossenbol, dus hij geeft het werkt niet 100% perfect, maar je ziet eigenlijk dat het relatief weinig werkt. Dat je toch gewoon vrij makkelijk de bossenbollen uit te halen met een bepaalde zekerheid. Zo eigenlijk alles wat met objectdetectie te maken heeft en waar wij aan kunnen denken, kunnen we tegenwoordig wel met zoveel oplossingen verbeteren. Maar weet die computer nou echt dat het een echte bossenbol is? Nee, een computer die heeft in principe geen begrip van een bossenbol, zoals wij wel. Wij weten van oké, het is een bakje. Het gaat puur om het visuele. Hij weet hoe een bossenbol eruit ziet, maar hij weet niet wat het is. Dus we kunnen.
All right, so for the non-Dutch speaking people, we created a model that was able to detect these pastries, and turn sound off for the rest, for the remainder of it. And basically, you can train such a model. We did this within a day. So this is pretty easy. There are two things you don't want to eat in the Netherlands on TV, bossenbol and a tompoes. And here you made them eat a bossenbol and then talk, which is the worst version of it. But it's quite neat to see this. We also did other stuff on, for example, soccer player detection, but given the time, we skipped that one. But I did promise you that I would still show you the video of the bridge that's being cooled. So this was a really cool project for us because it really has a large impact on how often these bridges need to be cooled, that they only cool them on the right days, not too often, but definitely also not too few times, because these boats, they're actually quite expensive to rent for a day. The water is pretty cheap because you can just suck it up from down there. So that's not the problem, but to rent them and to make them run is quite expensive. A more famous example from these days, this is actually a self-driving Tesla in the USA, where a little bit more is allowed than in the Netherlands or in the European Union. So in the European Union, these cars, they stop by themselves for stop signs, for example. So here you'll see it stopping itself. And yeah, like I said, it's in Europe, it's not allowed. It has to keep going there. It cannot just brake if he thinks he sees a stop sign because they're just too afraid still. But I personally, I have a self-driving car and I use it 95% of the time. So I'm pretty confident in the system, especially when you have two nice white lines that you just need to stay between. That's fairly simple for such a car, and you arrive a lot more relaxed. I already said I did fraud detection at ING. This was actually my first news article while I was at ING doing my fraud detection. There was a guy, he stole 25,000 euros from the ING bank using a smart trick. We detected it. He stole 200,000 euros from the NS. They never detected it, but he got caught while we were analyzing his bank account. And there are, of course, a lot of useful and less useful applications for AI. Winning drone races is one of the less useful applications, I would say, but they've shown that it can do it faster than a computer or than a human. And a lot of people would say, like, yeah, but it's pretty normal that a computer can do it better because it has sensors, etc. But what they are forgetting is that, yeah, of course you can do it faster with a computer, but not only that, it was trained automatically. So nobody really told it, the drone what to do. They just said, like, yeah, this is a good score, this is not a good score, you should improve, you should improve, you should improve. And whereas if you would always say to a human being that he should improve, 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 at some point you get kind of tired of hearing the same thing. But the computer system never gets tired of hearing that, and it will keep trying to improve and improve. Famous other example, the Boston Dynamics, the Atlas robot. I think they are getting away from it now. I think it's also because they're getting slightly bored, is my interpretation. So they just want to do new projects. But this robot is already more athletic than half of the Dutch population.
They got the electric. That's why they moved to the new generation. They moved to the new generation, which is electric.
Ah, I see. This was all pneumatic, or?
Yeah, I don't know exactly, but the new one is much more lean, can do even more stuff.
Nice.
Anyway,
yeah, they were quite large as well. Yeah. What I like about this video, of course, there's no sound here. It's a video in Dutch, but at some point, this lady says about the robot that he is so sweet. And I think that's great. If you can really give something like a characteristic that you would normally just use for human beings or at least living creatures, if you can say that about a robot, like for her, this is really entertainment during the day, and the robot shows up there and is nice and speaking to her like, hey, what you doing? Like just giving her company, because if you just think about yourself, like how often you visit your grandparents or depending on how old you are, your own parents, like, you cannot visit them all day, every week. So at some point, these people are there by themselves, and they might have friends there, but the older they get, the less friends they have that are still alive. So I think it's really nice if they can still have the feeling of social interaction, also with robots that are extremely patient. Like they'll listen to the same story for the 100th time in a row. It doesn't matter to them. So I think it's great. It's a great addition. It's maybe not for everyone, but I do think it's really nice. And if we look at the future, so what can you expect more? I think smart cities might be a thing that's coming up. I just added this for fun because this is also slightly AI. What's in here? This is actually the moment where Feyenoord becomes champion, and you see like, yeah, computer says goal, computer says goal. No, and nobody can argue because computer said so. And they are trying to argue, but he says no, computer said goal. So I think this is like both a warning and a fun part at the same time. Like, watch out that we don't go too much for this, but in this case it actually was a goal. The goalie pulled the ball over the goal line himself right after he stopped it in front of the line. So here he stopped it in front of the line, everything is good, no goal, and there he makes an own goal by pulling it over the line. Final champion, I was a happy guy. I already mentioned breast cancer detection, so actually computers are better at it than radiologists by now. And that's just one of the examples of where actually healthcare is being supported a lot by computers. And I always say computer plus people are actually still better than just a computer. So a couple more warnings. Face recognition, make sure you train it on all the data and not just on white males. as Facebook did. So Facebook was proven that they were better at detecting males and they were better at detecting white people than dark people. So those are things that people should really be careful about. I'll skip that one, it's too long. And also the tax authority can always use lots of data and request lots of data in the Netherlands. So whereas we always used to be scared of a police state, we should watch out that we are not turning into a tax state where the tax authority knows everything about you. So yeah, don't store information where the application is too small. One example of this, we were approached by a soccer club, and they asked us to store one of the things they asked us to store was the religion of youth players. And I said, why do you want to save that? And they said, well, yeah, if they have the Ramadan or stuff like that, then we want to know in the analysis. And I said, but how old are these kids? Starting from 8. I said, do you really need to register the religion of an 8-year-old? Is it really that important to you? Or should you maybe just like, not even if it's allowed by the rules, by the way, it's not allowed by the rules, but even if it were allowed by the rules, should you not just have some common sense about like, yeah, let's not store that? And that would wrap it up. 1 minute
Yeah.
over time.
Yeah, all good. Thank you, Victor. I really enjoyed the presentation. It was nice and was fun also. So I will quickly once again share this one slide to everybody about what we're doing, if that works out. So indeed, we did this by the Effective Data Foundation. So this is an initiative to share thoughts and best practices about data and AI. This is our first webinar. We intend to do more if people appreciate it. We don't have a direct goal rather than just share information and thoughts and experiences. There's various certifications around and a learning path. And well, we hope you enjoy this webinar. And if so, we might do more webinars. I think we'll do 1 or 2 more anyway, regardless if you like it or not. Well, thank you. Do let us know your feedback, and if you like to participate in the next webinars, please attend. And a big thanks to Victor. It was a really nice approach. No slides, just videos. It was really good. Thanks.
Thank you. Thanks for having me.
Okay, I see a few more thanks coming in from everybody, which is great. I will also clap hands. That's also fun to do. Does it work here somewhere?
Nice.
I don't see the clap some hands. And then, well, hopefully see everybody at the next time. Have a good day. Thanks. Bye-bye. Bye.
You too. See you. Thank you all.